All right, so we've been learning some of the basics about vectors, and one of the big things that's in the vectors unit that we are capable of actually using vectors for is solving application problems, is doing word problems. So the nice thing about the word problems is at this level especially, they're pretty straightforward, where you typically have one item or force or something in the problem, and then you have another force in the problem, and you add those together and find the resultant. So we have different things that can act as magnitudes, and so one of those is like how fast something is flying, or how fast something is driving, or how fast somebody's running. That would be a magnitude that you guys have seen from the assignment we did yesterday. Another type of magnitude could be the force that you have on something from pushing a box, and you might have seen problems similar to that if you've taken physics. I don't know if you could have taken physics yet, but they talk about the units of measurement for that being in newtons, and we also talk about like pounds as a force, as in like the force of your body walking along the ground, or the force of you pushing something could be considered pounds. Maybe that's newtons too. Anyway, so forces can be different measurements. So in all of those cases, those would all be the magnitude. And then for us, the direction is always going to come as something that's in degrees. So when we deal with vector applications, that means we're typically talking about 2, maybe 3 or 4 forces that are acting on something, and we want to see how they interact together. And so what I've done is I've set up one typical, this is a very typical flying problem, and kind of walk you through each of the steps. And then if you look at the rest of the packet, that's actually your assignment for tomorrow in class, and then you can take the individual steps and apply them to one problem all at once. So basically 1 through 8 breaks down the entire process from start to finish, and then you can use that process on the other problems. All right, so first we have a DC-10 jumbo jet that maintains an airspeed of 550 miles per hour in a southwesterly direction. So if we look at this, southwest would be right in here. And we know that if they didn't specify a number with the southwest, then we're supposed to say it's exactly in the middle. So southwesterly direction would be, from standard position, would be 225 degrees. And it's important first for us to translate the number from real world compass markings into something that our calculator can work with. So 225 degrees is the calculator measurement that we're going to be using. Next, it says to write the vector that represents the magnitude and direction of the jet. So the magnitude of the jet is the 550 miles per hour. And we want to use this equation that we've worked with in the past. So I'm going to say the vector of the jet is the magnitude 550 times cos 225i plus sine 225j. And if you guys remember the assignment from when we did the measuring angles, if you had a number that was on the unit circle, then I asked you guys to simplify that. For these application problems, do not simplify, because you don't need to. It's not your final answer. You're going to get to the very end and have something else. And so these problems are strictly calculator active. I'm not ever going to ask you to do this by hand, because that's unnecessary work. So that means that the vector that we're using here is going to be 550 cos 225i plus 550 sine 225j. All right, so now what is the angle of the wind? So now we can read that part. It says the velocity of the jet stream is a constant 80 miles per hour from the west. And you can look up jet stream on like Wikipedia or something. It's actually like, it's not from the jet. It's not air from the jet. It's a jet stream is like a stream of wind that kind of goes around the world. I thought it was interesting when I looked it up a few years ago, but I can't remember the exact definition now. Anyway, look it up if you want. So, but that wind is 80 miles per hour from the west. So if we draw that, if it's coming from the west, it's coming from here and going this direction. So that means it's going towards the east. And east is 0 degrees in standard position. So here we're going to go ahead and write the vector that represents the jet stream or the wind. that's acting on the airplane. And so we're going to have 80 miles per hour. So 80 times cos 0I plus sine 0j, which gives us 80 cos 0I plus 80 sine 0j. Okay, so, and this is a similar procedure for every problem. So draw a picture of the situation and then write your angle in standard position and write your vector. Draw a picture of the angle, write the angle in standard position, find your vector. Now it says the vector that represents the magnitude and the direction of the jet and the wind combined is going to be the resultant vector, which is what you get when you add the two together. So I'm going to say the vector of the jet plus the wind. And when we add two vectors together, we add the horizontal components together and we add the vertical components together. So I'm going to say this plus this. So I've got 550 cos 225 plus 80 cos 0. That's my new I. So I'm adding those two together, plus the vertical component, so 550 sine 225 plus 80 sine 0 j. Okay, and at this point, this is where we get our calculator out. So we're not going to deal with continuously writing this anymore. And I will say that for the rest of these problems, you can do almost everything exclusively in your calculator without writing anything down, and I do not want you to do that. I want to see all the work. I want to see you writing out this vector. I want to see you writing out this vector, and I want to see you writing out this vector. So I want to see all that work written out, and it is annoying, but it will make you remember it better, I think. So 550 cos 225, and of course when we're doing this, we're making sure that our calculator is in degrees, because if it's in radians, you're going to get really frustrated really fast. So negative 308.909i, and this is a decimal that I'm going to be using later in the problem, so I'm going to go ahead and store this, and I'm going to go ahead and store it as x because I always think of x as being a horizontal number, so left and right. So I'm going to write down that I stored that as x, and then I'm going to go ahead and be plugging this back in. So if you hit second enter, then it pulls it back up on the screen for you, or I guess you could have gone up and highlighted it. Whatever you want to do to type it in again. So now I'm typing the exact same thing with sine minus 388.909j. I'm storing that as y. Now the reason it's good to write these down is because if you make a mistake on a test, then I can figure out where your mistake is to give you partial credit. It's literally the only reason I want you to write it down. Okay. Find the speed of the jet and the wind combined. This is the actual speed known as the ground speed. So the speed that the jet is flying is like the speed that it's trying to fly, but when the wind acts on it, it's going to either slow it down or the wind could push it along and make it go faster. So speed in this situation is magnitude. So what we want to do is we want to find the magnitude of the jet and the wind combined. So this is what we're doing next. We're doing the square root of negative 308.909 squared plus negative 388.909 squared. And what that really means is that what we're typing into the calculator is x squared plus y squared. So I only wrote this out this one time. If you look at my answer key for the rest of the problems, I went ahead and I wrote this. But this is important to write in your notes so that you don't forget what you're doing here. So square root of x squared plus y squared. So that's what I'm typing in. Again, we're never using rounded decimals. We're only using stored numbers here. And so I get 496.663. That's the speed of the airplane now. And this is in miles per hour. So it looks like the wind slowed down the plane a little bit. Okay, now it says to draw a picture of the vectors. So draw a picture of the first vector and the wind vector and the resultant vector. And that's because it helps give us an idea of where our final answer should be as far as what direction the plane is going in relationship with the wind acting on it. So we know that the plane was going in a southwesterly angle, and it was 550 miles per hour. And since that 550 is the magnitude in this case, that 550 kind of represents the length of the vector. So southwesterly, 550 is going to be pretty long. I might have made that too long. I think it's okay. All right, so then down here, I'm going to draw another x and y coordinate right down here, because now I have to think about the wind acting on this. So this was Vj, velocity of the jet, plus, and so now I'm going to add to it the angle of the wind. And the angle of the wind was that 0 degrees, and it's only 80. It has a magnitude of 80, so it's a little bit less than 1/5 of that distance. And again, this picture does not have to be perfect. It's just to give you an idea of where your resultant vector should be ending up. So that means that my resultant is right here. So that's the velocity, or the vector of the jet and the wind together. So I know that I should have an angle in the third quadrant. All right. Now, when we find the angle for any of these application problems, we're not going to be looking for the angle between two vectors. We're looking for just the angle of this resultant vector in standard position. So instead of using that weird cos formula that we use to find the angle between two vectors, we're actually going to go back to like old school, like what we did in the trig unit. And if we want to find an angle, we're actually going to use SOHCAHTOA. And the reason we're going to use tan is because tan theta was always the y coordinate divided by the x coordinate, and we have a y coordinate and an x coordinate right here. If you write a vector in standard position, then that means that this coordinate of the vector was 0, 0, and this coordinate of the vector really would have been that x value and that y value. So that makes it really easy for us to now find the angle. So we're going to say tan theta equals y divided by x and if I want to solve for theta, then I just need to do tan inverse of each side. So we know that tan inverse of y divided by x is going to give us our answer. So I'm going to say, I'm showing my work so that I can look at this in the future and know what I did. But in my calculator, I'm just going to type in tan inverse of y divided by x. That gives me 51.540. Okay, so a 51 degree angle is up here. That's where 51.540 is. So it looks like our calculator gave us a wrong answer, and that's not the case. If you guys recall from back when we learned about trig, we found out that when we do tan inverse, we are only ever going to get answers that are in quadrant 1 and 4 from the calculator. So if we want to get another answer for tan, we have to, if we're in radians, add pi to get the other answers, but we're not in radians, we're in degrees. So we're going to add 180 to get the other answer. Now the reason you draw the picture is so you can figure out if this answer the calculator gives you is right, or if you need to add 180 degrees and put it on the other side of the unit circle. So, and it will be one or the other. It's never anything other than that. So the nice thing about these problems is that like half the time the answer is what you wanted it to be. But in this case, we got to fix it. So I'm going to add 180 to this to put it over into the third quadrant. And so that means we're talking about a 231 degree angle. So from standard position, that was 231 degrees. So I'm going to go ahead and add 180, and I get 231.540 degrees. Okay, now in this problem, we have the standard position But we always need to go back and write the problem in terms of like compass directions. So if the original problem references bearing, then you should put your answer as bearing. If the original problem references like north and south, then you should phrase the answer that way. So if we look at this problem, it said southwesterly direction and it talked about west. And so this, if we look at our result, it's an angle that's a little bit to the west of south. And so that's how we're going to write our final answer. So what I need to do, instead of writing the angle the way that I wrote it, I need to figure out what this little bit is right here so that I can write the angle as a southwest angle. So south something west. So what I'm going to do is I'm going to take 270 and minus off the answer that I just got, because I know that if it went all the way down here, it would have been 270. And so it's a 38.460 angle. So south 38 degrees west. Okay. So at this point, when you guys are doing this math and finding these answers, I would like you to round to 3 decimal places. But the last step is to write the answer in a full sentence. And when you do that, I would like for you to take these answers and just round them to the nearest whole number. So anytime we do a story problem, we're going to write a story answer. And so here I'm going to say the ground speed of the plane is about 497 miles per hour in the direction south 38 degrees west. All right, and so that's the general process we're going to use always when we do application problems, okay? So at the very top of our paper, we're going to go ahead and write down kind of a list of what we did. Apparently there was chocolate on my desk. I don't know if you can see that. Can you see that? Smear? Nope, give it a second. Focus. There we go. That's a chocolate smear right there. All right, so first step is to write each vector using angles in standard position. The second step is to add the vectors together. The third step is to find, I don't need to write 2, find magnitude, which is the square root of x squared plus y squared, and direction, which is tan inverse of y over x. And then fourth step is to write the sentence. So this is pretty common for the problems to just kind of work out this way. All right.